Right. Yesterday we were talking about we started our lag lead compensator example, and we're going to finish that today. So just a quick reminder on lag lead design, we start with the lead design first, which changes the root locus shape, and we want to adjust the root locus such that it passes through the desired closed loop pole location. And then after that, we add a lag compensator, which preserves the shape of the root locus but reduces steady state error. Um, you might notice on your homework that when you're adding your lag or your PI compensator, that your settling time has suddenly increased. It's because of that dominant pole you added close to the origin. By adding a pole in zero, open loop pole in zero close to the origin, you have basically like a self-contained branch. Uh, where that closed loop pole is going to be close to the origin, and because of that, we have a really slow decay rate. So even if your PD or lead design works well for your transient response, your settling time is going to be a lot slower once you add your lag or PI compensator, and that is normal. Oops. Okay, so yesterday we started this example where we're trying to reduce the settling time by half, and while maintaining 20% overshoot and reduce the steady state error by a factor of 10, so 1 over 10 of the uncompensated system. And we were able to find the lead pole with a arbitrary lead zero placement. And from that point on, that's where we stopped. So now we're going to move on to the lag design. If I were to, and maybe I'll do this all at the end on MATLAB, what I would do is I would check if this is valid, if this design works. But I'm going to I'll just provide you the code for it after. But if we look in MATLAB, we find that we get from MATLAB, and maybe to write it out so you can see what I was doing. I would do R locus of S plus 5, so my lead controller multiplied by G. And I found that K lead is equal to 1,360 to get that where I get 20% overshoot at the desired pole location. I think from MATLAB the numbers were my TSU was 2.19 seconds, and my settling time of the compensated system was 1.10 second. So then what we're going to do now is we're going to add a lag compensator. And we're going to reduce it by, we want to reduce ESS of the uncompensated system, or ESS of the compensated system should be 1 over 10 of the uncompensated system. And this is a type 1 system, so it's going to be a error for ramp input. Now, by adding a lead compensator and having some gain, we have changed the steady state error of the uncompensated system already. It's likely that's going to be less, it's going to be smaller. So we need to calculate the lead compensator, the steady state error of the lead compensated system. So the lead compensator has changed ESS, where ESSU of the uncompensated system is going to be 1 over KVU. And that's going to be, this is the constant for ramp input, where KVU is equal to the limit as S goes to 0 of S times our K times G of S which is 192 times G of S. Which is equal to limit as S goes to 0 of S times 192 multiplied by 1 over S times S plus 6 times S plus 10. So the 192, I believe, was, did I provide that earlier? Let's see. Yeah, so from earlier, I did find K is equal to 192 based off of our locus from root locus of the uncompensated system. So that's where that 192 comes from. So then these two cancel out, and we get KVU is equal to 3.2. Okay, so then our error of our uncompensated system is going to be 1 over 3.2, which is roughly equal to 0.3125. So then our error of our compensated system is going to be 10 times smaller, so it's just going to be 0.03125. So this is our target. We want steady state error to be this small. So then now let's check the steady state error of the lead compensated system. All right. So for the lead compensated system, we get ESS lead. I'm gonna just write LD here for the lead compensated system. And it's going to be 1 over KV lead. And it's the same equation where the KV for the lead compensated system is now going to be limit as S goes to 0 of our lead system, which is going to be 1,360 multiplied by our lead compensator, which is S plus 5 divided by S plus 19.8. Well, apologies. I'm missing I need to multiply this whole thing by S as well. Multiplied by G of S. All right, I'll just write that out. 1 over S times S plus 6 times S plus 10. Again, the S's cancel out. And then we're left with 5.72. So then because we added our lead controller, we now have a smaller error of 1 over 5.72, which is equal to 0.1747. So by adding a lead compensator, we have changed the steady state error, so we actually need to reduce the steady state error by a smaller factor. We don't have to reduce it by 10 times. We need this value to get to 0.03125. Are there any questions? Okay, so then we have to then determine the reduction needed from going from the ESS lead to ESS compensated system. because from there we can determine our zero to pole ratio for the lag system. So we're going to take the ratio of this, ESS lead divided by ESS compensated, which is going to be equal to 0.1747 divided by 0.03125, and we get 5.59. So we need a 5.5 or 5.6 times reduction from the lag compensator to get this final number of 0.031. Okay, so then we now have to design a lead compensator or design a lag compensator. To reduce ESS lead by 5.59 times. Okay, so we're going to design that by choosing C lag is equal to K lag divided by S plus ZC over S plus PC. And so I write out K lag, but I just choose K lag to be equal to 1 because our root locus shape is preserved. So the gain that we pick from our lag lead compensator is going to be pretty similar to the gain that we used for the lead compensator. And then we're going to just choose that K lag lead is equal to K lead. All right, so then this is going to be for at the last step. So what we're going to do is we're going to write out so we know that we need to reduce the steady state by 5.59 times. So we know that KVC is going to be 1 over KVC is equal to 0.031. And yeah, 3125. And we know that KVC, when we write it out, that's going to be equal to the limit as S goes to 0 of S multiplied by our C lag of S multiplied by C lead of S multiplied by G of S. Yeah, so we choose K lag to be equal to 1. Mainly because so let's say we have I'm gonna draw two different root locus on the same plot. So this green one is like one root locus of the system. And then this red one is also of a second system, but now we have a lag controller right there and right there. So now we have a slightly different root locus. I mean, look maybe more like this. Not exact, but something along the lines of that. Okay. So the red has the same poles as the green, but now it has an added pole in 0 right there. And that's our lag compensator. And because the main property of a lag compensator is that we maintain our root locus shape. So if I were to choose like this gain K is equal to 10, and it's at this point here, Our same lag system would also have K is roughly around 10. So our K lag is roughly equal to our K in this system here. Or or in other words, when I'm doing the R locus of this plot here, it's going to be of S plus Z C divided by S plus P C multiplied by G of S, which is going to be in green, which is the original system. And when I find the gain at this spot here, it's going to be roughly equal to 10 as well. So when I choose a gain for a lag compensator, I actually just choose unity because it doesn't change the root locus shape that much. So I just use this. Yeah, I just use the gains from the lead compensator design. I hope that answers your question. So we can always choose one. Always is an absolute, but I would say 99% of the time, yeah. The we can You can just choose one for the sake of this class. Uh, because in the end, we're going to choose this for our lag lead comb. Yeah, yeah, yeah. Just for this class, you can just choose one. Technically, this would probably be more like maybe 9.8, but because all of this is based off of approximation, it does not matter. Choosing 9.8 versus choosing 10 is going to be observable in MATLAB, but in real life, you're not going to be able to observe the difference in the transient response. Okay, so we're going to write this all out. We get limit as s goes to 0 of s multiplied by so then here we can choose our whole and zero if we want, but I'm going to just write this as a ratio. So then I can generalize this solution. S plus PC and S plus ZC multiplied by lead, which is going to be 1,360 multiplied by S plus 5 divided by S plus 19.8 divided by 1 over S times S plus 6 times S plus 10. S's cancel out. And then we're left with this. ZC over PC multiplied by, and if you actually look at this value here is going to be KV lead. So KV lead is equal to KVC. So then we get this ratio KVC over KV lead, which is equal to the steady state error of the lead divided by the steady state error of the compensated system. So they are flipped, by the way, intentionally, which is equal to ZC over PC, which is equal to that 5.59 ratio. So the reason why these are flipped is because ESS lead is going to be 1 over KV lead. So this is the ratio of our zero to pole for our lag system. So if I pick, let's say if I pick PC is equal to 0.01, then I have to use ZC is equal to 0.059. I could also pick zero point 0.1 and I get 0.59 as well, and that's also okay. So my compensated system or my lag lead system is going to be this 1360 multiplied by my lead controller, S plus 5 divided by S plus 19.8 multiplied by S plus 0.0559 should be 559 divided by S plus 0.01 multiplied by 1 over S times S plus 6 times S plus 10. This is my final system.
Picking the pole in order, we can just like pick some arbitrary small.
Yeah, you can pick an arbitrary small. You're limited by the actual hardware of where the pole can be based off of resistor capacitor choices, but for this class, any value you want is fine. I avoid anything smaller than that, 0.01. I mean, I would just do 0.1 because we're going to be dealing with a very long transient time. Because we're trying to reduce the sailing time by half, but now that I've added this pole really close to the origin, basically right here, we have this really slow decay. And because of that slow decay, our selling time is going to be a lot longer than our design spec, which is okay. And so in the homework, it's okay if you don't meet the design specifications, so long as you follow the steps. Maybe I'll really quick, I will show you the MATLAB code. I didn't load it before class, so it's going to take a minute. Well, anyway, while MATLAB is loading, I think. Okay, it's loading. I'll just recap this. So this is a nice table of, oh boy. Okay, there you go. So this is a table that summarizes PI, lag, PD, and lead control. So really, I think it's a useful table that gives you a short description of everything we covered. And then also this is for lag, lead, and PID controller design and the characteristics that goes with it. I guess here's the big picture of it. So I talked about it a few lectures ago. You may not have remembered. PID compensators have been around for a century. The first application was in automatic steering of ships in the 1920s. And the reason why we like it so much, and I think over 90% of the industry uses it, is because you can use it for a unknown model. So we don't use root locus techniques when our model is unknown. So instead, you just need to know how to tune the gains of each component and understand what it does. Because what it does is it uses error as feedback. So our output is usually what we get, but our input is what we want. So it's very robust because of that. And it's very easily tunable. There is limitations. Controller uses feedback to track error, which means that PID controller is reactive. An inherent weakness of feedback systems is that you're always behind. So if you have oscillation, you can't get rid of the oscillation. Not knowing the plant model means control op may not be optimal, and you might have a lot of very unoptimal inputs. It's sensitive to noise because of the derivative component. So you need to also filter your feedback signal. And so I talked about a little bit, cannot remove periodic disturbances because when you have oscillation, you have feedback, you're never going to catch up. And you only control error. So you're not you're only trying to reduce the error. And this is what a actual analog PID controller looks like. I would not know how to derive that, but that's what it looks like if you're curious what it looks like before things became digital. Yeah, and here's some just takeaways before we move on to the MATLAB and chapter 10, which is Bode plots. So PI and lag compensation preserves the root locus shape by the addition of a pole and zero close to each other near the origin. Note that they do become the dominant poles, and they do make your system have a decay response long term. PI and lag compensation is used to reduce the steady state error. PD and lead compensation reshapes the root locus such that we cannot move the root locus to pass, such that we can move the root locus, or I would say like reshape it. So we move the root locus pass through the desired closed loop poles that was not attainable in the original root locus. They also improved the transient response, and because PI and lag controllers generally preserve the root locus shape, we designed the PD and lead compensator first to get our new desired root locus shape. Then we add the PI and lag compensator. One last thing I should probably write on here is that all of the design here is based off of second order approximation, but it is not necessarily correct. If you use step info, which you might have seen from homework, what you got from step info and what you calculated is different, and that is also okay. All right, so I'm going to jump to chapter 10 after a quick demo. I need to. I definitely was not prepared for this. Let's see. So this is our lag lead system, and this is our uncompensated system. And I created the root locus for it, and I got. There you go. So I was able to find 192 for 20% overshoot, which I don't know, somewhere around here. 192, close enough. Okay, so then from there, wow, I got 192.1. I'm going to get rid of that. Okay, so then from there what I did was I then plotted the uncompensated system with a gain of 192, and can't really see it because there's error, but if I were to zoom in here, you can see that there is error. The lines are parallel, meaning that the steady state error is constant. Okay, so then we found that for the lead compensated system, I got, this might be a different problem. These are different values. All right, so let me fix this on the fly. We got what, 5 and 19.8. Yeah, I'm gonna just check 0 minus 6 minus 10. Okay, we're good. Okay, we're good. And then from there, we found it was 1,360. I wonder why I changed these values. Oh, you know what? When I first taught this class, I did pole zero cancellation. I used S plus 6. That's why the values are different. But nope, I like to, well, yeah. Anyway, so now that we got that, we rerun this, we can see that the lead system, the ideal scenario. So even though this is a type 1 system, we want to look at the peak time. So where you can see here, I have visible reduction of the peak time. And then from there, we need this node is very outdated. It was a 5.59 reduction. And I wrote this such that it would automatically choose a zero lag, zero for me based off of my pole that I chose. And then I'm going to just use K is equal to K lead. We're just going to maintain that. Okay. Okay, run that. Okay, KS. Okay, we're going to do that. Then run that. And run the next one. Okay, and then, so now we have the full system. Hope it works. Okay, so I guess it's kind of hard to see if we actually have had any marginal improvement. But if we look here, I guess the compensated system is better than the uncompensated system. I don't know if that's a 10 times reduction, but if you check here, it definitely is not a 10 times reduction. So maybe if I were to check out here at 100 seconds, You see now? Now we have a 10 times reduction there. And the reason why we have that large of a gap is because we added that pole in zero really close to the origin. So it has a really slow decay to the final value. And in this case, it's taking a really long time to decay to that final slope that we created. And it would take roughly maybe 50 seconds because we're dealing with what, e to the minus 0.01 t decay. So if you see that your plot is not responding or it looks like it's responding slowly, I would just increase your time scale because even at 20 seconds, you can see that the error is still converging to its final value or final slope here. It's only at like 70 seconds. You can see that. Looks about right. All right, so I'll upload this code online. If you want a different example of this same problem with pole zero cancellation, the textbook does do that. As All right, so now we can start chapter 10. Chapter 10 is going to be broken up into two parts again. I've uploaded the first part and the second part will be uploaded soon. Oh, that's just from 2023. It's not updated. Oh well. Okay, so frequency response techniques is the main uh content of chapter 10. Chapters 10.3 through 10.5 is Nyquist stability criterion, which I will also talk about on a separate slide. I would say of the two parts, this is probably more important, Bode plots. And so we're gonna go through an introduction first. Hold on, I'm waiting to actually load the newer slides on it, so give me a sec. Apologies. Not sure why the new one's not on here. Yeah, that the slides I have is from last year, but I do have some corrections and modifications from last year. So I'm going to, I think because I named them the same from every year, so I think I might have just sent the ones from last year instead by accident. And I don't want to give you all the old slides because it's outdated and might have some error. 2024. Yeah, so so that's why I'm going to what I'm going to do is I'm going to download it from Canvas. So we'll have a impromptu 3-minute break. Because unfortunately I do not remember if where I made errors and from last year because it was a year ago. So I'd rather not use old slides. Okay, got the new ones loaded. Thanks for waiting. All right, we do not need to see my face that close. All right, so when we talk about this, so I guess the purpose of chapter 10, it's like really it's useful for analysis because when we don't know system models, but we can excite it with known inputs and observe the output, we can estimate how the plant behaves. This is one of the, I guess, beginning ideas of system identification where we observe the output and inputs, and then we're able to build a model from it. This is my personal take. I think this is the most important chapter for this class. besides chapter 9. I think this is more important for research. Bode plots are used in research papers, so you do need to know how to read it, and it's crucial. It's also crucial for field and robust control. This also Nyquist stability criterion and Bode plots both relate to robust control. So basically, it tells us how much uncertainty can our controller handle before our system is uncontrollable and unstable. One other thing about Bode plots and the Nyquist stability criterion, which is covered in which will be covered later on, is that you can, when your system has delay, because all digital systems will have delay, you cannot just check the poles of the system and see if it's stable. When you have enough delay, the system can become unstable even if you have stable poles. So that's why I think that this is actually more of a useful mark for stability than just checking the poles. Okay, so yeah, so Bode plots, you can use it. It's used on systems, linear or nonlinear, to learn what frequency is excited. And from there, you can get something called a gain and phase margin. And basically, your gain and phase margin tells you how much gain your system can have, like how much gain you can increase to that system before it becomes unstable, and how much time delay, which is defined by a phase margin, like how much time delay you can have before you have instability. So you're able to do that through Bode plots and through the Nyquist stability criterion. So we're going to go through chapters 10.1, 10.2, and 10.7. And this is going to be a fairly long chapter. So we're going to go through some definitions in the introduction. So the frequency response looks at how a system responds when it's excited at a certain frequency, and it's useful for nonlinear systems because if we have an input frequency, we might get a different frequency on the output. Uh, and then we use data from frequency response to build a model. That's kind of like the idea of system identification. And for linear systems, in this class, a sinusoidal input will generate an output with the same frequency, but when I say likely, different amplitude and phase. So there are cases where we can have the same amplitude and phase, but most likely it's going to have a different amplitude and phase, but the frequency is going to remain the same. So that's going to be the case for all linear systems. So for this class, we can make that assumption. So if we look at a standard mass spring damper system, if our input is of magnitude mi at some frequency, our output's going to be at a magnitude of mo at the same frequency, but with a phase shift. And the phase shift is denoted by the phase here. These are a phase shift. So if I put a sine input, I get a sine output for this mass spring damper system. And if I continue having that oscillation, it's going to keep shaking until I stop. So we can represent sinusoids as a complex number called phasors. So we talked about that in chapter 9 briefly, but we can represent like this, where we have mi times some sine wave is going. We can represent it as this, where it's mi as the angle of phi and at that frequency. So all of that information can be rewritten here as a phasor. The magnitude frequency response is the ratio of the output magnitude to the input magnitude of the sinusoidal response. So this is one of the components we need for our Bode plot. And then the phase response is the difference between the phase angles of the output and input signals. With the phase response, we're always going to have a phase delay, meaning that when we put something into a system and then we watch it react to it, it's not going to react before the input. So there's always going to be a phase lag. We always have a phase lag. Locally, we might have a system where the phase is ahead, but overall, the systems is always going to be in phase lag. All real systems. So here's an introduction. Here's a generalized system where if we have a input u of t and our output is y of t, we can actually write this whole system with these two. So in the past we've had sine, ramp, or parabolic, or we mostly just do step and impulse inputs and occasional ramp inputs. Now we're going to be doing sinusoidal inputs. And one easy thing about sinusoidal inputs is that if we have a sine input going in, we get a sine input coming out with a different phase and magnitude. So this generic expression holds true for all stable linear time invariant systems. And using this expression, we can plot the magnitude and phase as a function of frequency. And this is what's called a Bode plot. So this is helpful in helping us determine that the system has a range of frequencies that amplifies or attenuates the input. Are there any questions so far? So this relates back to the Tacoma Bridge incident. If they were to just draw the Bode plot of it, they could probably see like these peaks where there's going to be resonance. Using Bode plots, they could have determined that. So we're going to move on to Bode plots now. So in MATLAB, you can use the command Bode. It's probably something similar in Python as well. So the Bode plot is a graphical representation of the transfer function's magnitude and phase as a function of frequency. And when we plot it in the magnitude plot, we do it in the decibel scale, where we take the log base 10 multiplied by 20 of our magnitude. And this magnitude is going to be the output over the input magnitude. So MJ, as a reminder, M is equal to M output divided by M input. So then it's going to be in log scale, log base 10 scale, which is also known as decibels. Some places might do 10 times log base 10. It does not really matter because it's just it's just scaled then. And there's two things you need to know about decibel scale. When it's below 0, we call it attenuation. When the magnitude is above 0 decibels, it's called amplification. So when we have a magnitude that's like -5 decibels, where that means our output signal is smaller than our input signal in terms of magnitude. And remember, because it's a log scale, if we go from 0 to 3, or 0 to -3, that's going to be a reduction of magnitude by 50%. And so if we go to 0 to -10, it's a much larger reduction. It's not linear, it's a log scale. Okay, and the same with the phase plot. When the phase is greater than 0 degrees, it's called a phase lead. And when the scale is less than 0, when the angle of M is less than 0, it's called a phase lag. So this is where lag and lead compensator names come from. A lead compensator is when we have phase lead, and then a lag compensator occurs when we have phase lag. And the pole and 0 position relative to each other will cause either a phase lead scenario or a phase lag scenario. And we will draw that out later. So then in the X scale, which is going to be, because we're plotting this against frequency, the X scale is in frequency and it's typically done in log scale as well. So we're gonna just jump right into an example of drawing a Bode plot of S. G of S is equal to S plus A, where we assume A is going to be a positive number, meaning we have a 0 at -A. And then I'll also ask you how the plot will differ when A is less than 0. So we're going to start with this first case where A is greater than 0. And I mean, it's pretty straightforward. All you have to do is just find the angle and magnitude of G. So when we draw the Bode plot, actually, I'm not sure if I talked about earlier. Did I define it earlier? Okay, so I did have it here. When we draw the Bode plot, we don't look at the real part of we don't consider the real part of the S of the S term. We only look at the imaginary part, which is the frequency component. We don't look at the transient response. We only care about the oscillating response. Once we get to there's no steady state value, but I guess the steady state response is going to be an oscillation. So we always evaluate when we draw the Bode plot, we always deal with S is equal to J omega, and we ignore the real part. So we're going to be evaluating G at J omega, which is equal to A plus J omega. So I'm breaking it up into the real and imaginary parts. And basically the magnitude is going to be this. It's going to be the magnitude of G at J omega is equal to the square root of the real part squared, which is A squared, plus the imaginary part squared, which is omega squared. And one thing about omega is we always assume it's going to be greater than 0 because it's a frequency. We don't have negative frequencies. So we don't evaluate the negative parts. And it's not going to be equal to 0 because if you have 0 frequency, then that's just a step input. Okay, so that's it. We're done. For the phase, and now that we've done root locus, I hope you know how to find the phase. The phase of G at J omega is going to be equal to, I'm going to call it phi, which is equal to the arctan of the imaginary component, because that's the vertical component, divided by the real component. All right, and because this is always positive, because of my given statement here, this is always going to be a quadrant 1 angle. All right, we're done. That's it. So then now we just plot it. So we just create a bunch of values and we plot these as a function of magnitude to frequency and phase to frequency. But there are some strategic points that we look at, and we will just continue that tomorrow. Actually, no. Tomorrow is going to be a review for midterm 2. So we're not going to be talking about this. We'll continue this on Tuesday. So tomorrow I'm going to be reviewing material for midterm 2. And yeah, thank you.